In this video, we're going to continue our discussion on comparing two populations to one another, but we're going to talk about a different statistic with which we can do that. Now, the first half of this lecture may be review for some of you. You may have talked about this in your previous statistics course. Because I don't tend to talk about this in my previous statistics course, though, I'm going to assume that you haven't seen this. And we're actually going to start by talking about the one population version. Now, what we've talked about previously is doing one population and two population confidence intervals and the hypothesis tests, looking at means and proportions. And proportions are kind of an extension of the mean. However, there's another parameter that sometimes we look at, and remember, parameter is just a calculation on the population, like mu for our mean is the parameter. And in this case, the parameter that we can look at is sigma, that meaning for the standard deviation or variance more generally. Now we're going to tend to model variance mainly because we don't have a point estimate for the standard deviation that is unbiased. And I'm not going to talk about this really at all. I'll just mention that here. So we're going to go on and start with inferences about a single population variance. And then we're going to move on to inferences about two population variances. So thinking about this, remember variance is a measure of spread. So what these are asking is, can I determine the spread of a single population or compare that to a pre-hypothesized value or a fixed value? And then with the two population version, I'd be asking, well, can I make inferences about two of these and compare them together? So can I say that the variability in one group is more than the variability in the other group? Where this is really handy is consider a case where I'm looking for maybe a fiscal vehicle that I want to invest money in. Actually, this happens all the time. I don't just want to balance out my income, and I might compare two, and the average income for two might be the same. But if the average income for two potentially positive fiscal vehicles is the same, maybe what I want to look at then is, does one vary more often? Is one of these a more consistent return than another one? And if one is more consistent, do I prefer that or do I prefer the one that's more variable? Now note, with the one with more variable, as long as the means are the same, the one that's more variable is going to get some big shot returns and some smaller returns. The one that's more consistent is going to stay right around that mean or be closer to the mean than the first one. So we might want to compare two to see, is there reason to believe that one is bigger than the other? And then depending on what your preference is at the time, you could make a decision, do I prefer the more consistent outcome or do I prefer the more variable outcome? So in this case, this is just another example of when variance can be interesting. This is more of like a process control, and of course this class is called statistical process control. So consider if I'm looking to control the process of creating an output. So this is more not comparing two different things like the example we just talked about, but looking at a single variance, which is of course where we're going to start this lecture set. So if I'm looking at this single variance, maybe I want to make sure that the variability in my product is under a certain amount. So you can think here that if I'm filling up different bottles with detergent, I want to make sure that I'm sticking pretty close to my specified value, because if I'm doing too low, underfilling, then my clients are going to complain, and if I'm overfilling, then I'm wasting money and giving clients free product. Now the trick with this is that we're going to be doing different equations, different formulas. These are going to look very different from previously. It's not the similarity that Z and T had before. And we're also going to be using a different distribution. So the distribution we're going to be using is called the chi-squared distribution, and it is very closely related to the normal distribution. And what's interesting is that if I look at the relationship between the sample standard deviation and the population, excuse me, the sample variance and the population variance. Variance is s squared. Standard deviation is just the s. If you're not familiar with that, go on and write that down somewhere. Sigma squared is the variance, sigma is the standard deviation, and then s squared is the sample variance, s is the standard deviation. Have that jotted down so you don't get confused when I talk about this. But I'm going to be looking at the variance term, s squared, from the sample in comparison to the population. And this n minus 1 is just a relational factor that has to do with how these are calculated. So if I look at this ratio, this ratio is distributed as this new distribution, this chi-squared distribution. And we are going to have a degrees of freedom associated with this, just like we had with the t. So the t degrees of freedom was n minus 1 for a single population. It's going to be the same thing with chi-squared. Now, just like the t distribution with different degrees of freedom, the curve looks different. It's the exact same thing with chi-squared. With different degrees of freedom, our curve is going to look different, but this is how we're going to be modeling. And again, the big goal that we want to look at is the distribution of the the distribution of the sigma squared here. This is what we're hoping to look at. All right, so looking at this curve, so again, we've got all these different curves depending on the degrees of freedom, which is set by the sample size. So looking at these curves, if I'm making a 95% confidence interval, or remember this is generic, so I can make a 99% confidence interval and then put the 0.1 over 2 on the left and 0.1 over 2 on the right. So splitting up my error on the left and right, I could make a 90% confidence interval and put 5% of the error on the left, 5% of the error on the right. So this is true for all kinds of confidence intervals. But when I'm looking at this, one of the big things to note is that when I use this notation, this is now referring to the area to the right of the value. So this weird looking x thing is the chi, so chi squared. So you see chi squared. So I've got chi squared sub 0.975. This is indicating I want to pull a critical value from the chi squared distribution where 95% or 97.5% of the area is on the right. And that's what's going to give me my cutoff where 2.5% of the area is on the left. And again, the reason we do this for a 95% confidence interval is because I have to split my error on the left and the right. So I need to figure out where 2.5% of the error is on the left and then 2.5% of the error is on the right. And so again, because our chi-squared is looking at the area on the top, not on the bottom, chi-squared sub 0.25 is going to find that cutoff for where 2.5% of the area is on the right. Now this is for the table, so I want to be careful here because this notation doesn't necessarily follow what we've been using with our z and our t. So I do want to be a little bit careful here and clarify this. I personally tend to focus on the area to the left and the right because when we get into R, we can use that. But it's important that you can translate this from your table for things like your exams, if you're doing in-person exams. So do be aware of that. Do get comfortable with that table. We'll talk about it in a bit. And the table is pretty easy to look at. So I would focus on the area to the left and the area to the right. In any case, maybe what you can do is you can write a little L here. This is the left cutoff, and a little R here. This is the right cutoff. And again, associate these two. Why is this important? Because we're about to do some mathematical movement to get sigma squared by itself. And in that mathematical movement, it's gonna be a little bit confusing. So I want you to keep track of which one's this left cutoff and which one's this right cutoff, because I don't want you to get lost in this. All right, so why are we doing mathematical movement? Well, we're doing mathematical or algebraic manipulation of this because we really want sigma to be by itself. This sigma squared, this is what we're trying to find an interval for. This is the whole thing we're trying to guess, is what is the population variance? What is the population variation? That's the whole point of this confidence interval. So in general, what we can do is we can look at, okay, we've got the value over here on the left, the value over here on the right, and then the chi-squared is going to be in the middle. And then we've got our sigma squared that we know is distributed as that, we've got this ratio that we know is distributed as a chi-squared. So let's look at this. We've got the chi-squared is between these two values. All that that's saying is this picture. We've got the chi-squared distribution that we know is distributed between these two values, 1 minus alpha times 100% of the time. So 95%, if we have the cutoffs at these two cutoffs, then 95% of the time this is right. We could do this for 99% of the time or 90% of the time, whatever we want based on the alpha. So this is kind of our starting place. This is the previous picture. This is kind of the no-duh thing. It's kind of the definition of a confidence interval. So what we're doing is we're saying, okay, well, if this is the way in which a confidence interval is made, so we've got our chi-squared that falls 95% of the time between the bottom 2.5 and the top 2.5 cutoff. Well, if we plug in this value for that chi-squared, then this value is going to fall between those two values 95% of the time. And this is just a basic substitution. So don't think too much about this. The tricky one is, how do I get sigma by itself? And what you're going to end up doing is taking the inverse of all of these things. So how do I take the inverse? Well, you can do 1 over everything. The trick is, if you do that, so let's say I do 1, let me see, can I do this here? 1 over everything. The trick is, if I do that, the direction of the signs change. Okay. Now, when the direction of the signs change, you'll note that if you look down below, the directions of the signs are the same. So what we end up doing is, because the directions of the signs change, we put the smaller one first. So now, instead of the right-hand side being the smaller, if I do 1 over the right-hand side, now this is the biggest one. So I'm going to put this on the right instead of on the left. So I'm not just going to change the direction of the signs, I'm going to reorder this to show this in increasing. So it's going to be this one, and it's going to be alligator eats the middle number, and then it's going to be the middle, and then alligator eats the right number. But again, I want to go from left to right. So this value over here is going to get dragged down there. This one's going to get dragged here, and this one's going to get dragged over there. And again, you have to keep the alligator eating the right number. So if I move this one to the very left, the alligator eats the middle number. So alligator eating the middle number, and it's shown correctly in this bottom section. Then I go from the middle to the right. Well, if I'm moving the right all the way to the right, the alligator has to eat the bigger number, so the right one is supposed to be bigger. This one on the right is the biggest. So again, I want you to track with this. If it's throwing you off, don't worry too much about it. But I do want you to follow this, because this is how we get sigma by itself. And in fact, there's a typo here. I apologize. This should be sigma squared. So once I have 1 over all this, I end up in the middle with sigma squared divided by n minus 1. I apologize for my terrible writing. Wasn't really planning on doing this, but it's not too bad. N minus 1 times s squared. And then I've got 1 over chi squared sub 1 minus alpha over 2, and 1 over chi squared sub alpha over 2 on the opposite sides that they were, because again, the directions of the alligators change when I do the inverse. So when I do 1 divided by everything, and I'm left with sigma squared over n minus 1, now I just multiply both sides, or all of the sides, by n minus 1 times s squared. So that's why you get n minus 1 times s squared on that. It cancels out in the middle, and I'm just left with my sigma squared. And then I've got the over x chi squared sub alpha over 2, and chi squared sub 1 minus alpha over 2. All right, so now connecting back to what we had earlier, I had the left and the right side, remember, this is the left cutoff, this is the right cutoff. But because we've switched, now the number on the right is actually the left cutoff, and the number on the left is the right cutoff. And this gets kind of weird and kind of confusing, but that's why I had you write these underneath. So we can track it here, left and right, left and right. And then again, because we switched the sides going on here, now we've got the left cutoff in the bottom, or excuse me, the left cutoff, yes, on the bottom of the right-hand side of the confidence interval, and the right cutoff on the bottom of the left-hand side of the confidence interval. This is confusing. Yes, that's why I'm calling this out so much, and I apologize for taking so much time on this, but please, please, please don't get too confused. And follow along with this, and do keep this straight, because this will really throw you off if you miss this calculation. All right, so these chi-squared values that I'm talking about down here are all based on that chi-squared distribution we showed in the previous slide with n-1 degrees of freedom, same thing we had with the t. Now I've got sigma squared, so that's the variance. If I wanted to take the square root, then I can find the upper and lower limits for the standard deviation. I'm not going to go into the details on this, but you can do that, and that provides our best guess at a confidence interval for the population standard deviation. All right, so let's do an example. So in this example, we have a group of thermostats. In fact, my thermostat just broke, so this is a fantastic, timely example. So we're putting them in a room and asking it to keep it at 68 degrees. And then we're going to use 10 readings to figure out how variable this value is. And what we want to do is come up with a confidence interval for the variability of this, or for the standard deviation of the temperature within a room, given that we're trying to keep it at a constant temperature. So I've got my data. I can calculate my, let's see, so thinking about that previous equation, actually I'm just going to go back to that previous slide. Thinking about this, what do I need? Well, I need a value for n, I need a value for s squared. This is my parameter. This is what I'm trying to model. I don't, again, I'm never going to have that value. But I can find a value for chi-squared sub alpha over 2. That just comes from a table. And then this other chi-squared sub 1 minus alpha over 2. Now, in the t and z distributions, these guys were just the positive and negative versions of each other. But in this chi-squared, you see all of the chi-squared values were positive, if you noticed that in the previous graph. And if not, you can go back and look. So in this particular case, I'm actually going to have to look in the table a little bit more, because I'm going to have to find both of these values that correspond to one another. The table's not going to be too bad, though, so we'll see that in a second. So thinking about those, I can calculate my s squared, that is my sample variance, just from this data. I just do my normal sample variance calculation from this using my sample variance formula from our previous stats class. My n, my sample size, is going to be 10, and my degrees of freedom, n minus 1, is going to be 10 minus 1, or 9. So using this, degrees of freedom of 9, alpha 0.05, I can actually come up with my proper cutoffs. Now, what you'll see in the table is I've got 99% of the area in the upper tail, 1% of the area in the upper tail. So this is kind of the left-hand side cutoffs typically. Kind of cut right in the middle here. This is kind of the right-hand side cutoffs. Now, I have a total error rate of 0.05, which means that I want my error rate on either tail to be 0.25. So this is what we had earlier. 0.975 above gives me 2.5% of the area below, and 0.25% of the area above gives 2.5% of the area above. So these are going to be my two cutoffs. Now I'm going to scroll down to the 9 degrees of freedom line, and I'm going to see that 2.7 is my bottom left side cutoff, and 19.023 is my right side cutoff. But again, I want to be careful here, because the left side cutoff, remember, is going to get plugged into the right equation. The right side cutoff is going to be plugged into the left side of the equation, so I want to keep track of that. In the picture, you can see this is all we're doing. We've got 95% of the area in the upper tail. That gives me 2.5% of the area in the lower tail. And again, why am I doing 2.5? Well, I want to take my error rate, my total 5% error, and I want to split it between the top and the bottom. So if I've got 5 total percent error, I want 2.5% of the area to be below and 2.5 to be above. So that's why I'm using 2.5% below, is because I want to split that total error rate in half to put an equal amount in both sides. All right, so now I plug everything in. Oh, I guess I'm sorry I had this where I'm calculating the other one. We already found both of them in the previous table. In this case, this is showing you how you can plug these things in and then reverse do it. I wouldn't. I would just go in and start with the formula and keep track of the left and the right one. So starting this way and then kind of doing all those reverses that we just did, if you want to redefine the equation, can be nice because it can keep these from getting too confused. You'll have to put them in the right spot when you get sigma by itself. I think that's more work than you really have to do. So I would just go on and start with the equation and not forget to put the left cutoff on the right side and the right cutoff on the left side. I know that's confusing, but that's just how this process works. For the sample variance, again, you use your traditional sample variance formula or plug it into the magic box and you get 0.70. And then I just plug that into my equation. So I have n minus 1 times s squared divided by that chi-squared cutoff, and that's for my variance. So in this particular case, my variance is somewhere between 0.33 and 2.33. So this is my 95% confidence interval for the variance. And again, just like with all of our other statistical confidence intervals, I never know what this population variance is. This is a reasonable range of values based on my data that the population variance could fall. And so the goal is, because I can never know what this value is for all temperatures, for all thermostats, what is the true variability in the temperature? I'm never going to know that. I'm never going to have all that data. But based on a sample, I can come up with a reasonable range of values. And if I wanted to get more precise, I can get more data, and that'll give me a smaller confidence interval that's closer to this value, or that gives me a smaller range of reasonable values for this value by using more information to make this smaller and more precise. For hypothesis testing, this is going to look very, very similar to what we've had before. So in this particular case, just like before, we can compare to a hypothesized value. It's not as often 0 in this particular case because the variance can theoretically never be 0. So we are going to be using these sigma squared sub zeros to test the variance again, against a fixed value. As always, we reject if the p-value is less than alpha. But for our critical value, remember, if it's a lower tail test, we reject if it's lower than the cutoff. If it's an upper tail test, we reject if it's above the cutoff. And if it's a two-tail test, we reject if it's lower than the lower cutoff or higher than the higher cutoff. The only trick here is that if you're doing a two-tail test, it's no longer the positive and negative version. I mentioned that before with the Z and T. It was just the plus and minus version. That's no longer true in this case. In this case, you have to go and find both of these chi-square values on their own. So sigma squared sub 0 is this null hypothesis value that we're comparing against. The test statistic is going to be n minus 1 times your sample variance divided by this null hypothesized value. And again, you can see why we can't have 0 for this null hypothesized value, because we can't divide by 0. So this has to be an actual number for us to do this test. It has to be a number bigger than 0. And again, finally, degrees of freedom are just the same as the t, n minus 1 degrees of freedom. So putting this back together, we are looking for a variance of 0.5 or smaller. That's acceptable. So we're looking for evidence if it's bigger than that. I really don't like the way these questions are phrased because, again, these are phrased a variance of this or less. And the book is expecting you to know that because it could be equal to this, that's the null value. So what we're really looking for is if it's bigger than that. So this is status quo, and maybe that's a better way to think about this phrasing of a problem, is status quo is if this is satisfied. So we're only going to do something interesting if it's bigger than 0.5. So if we have evidence that it's bigger than 0.5. So in this particular case, that's what we're going to look for, evidence that the variance is bigger than 0.5. So we're going to do a hypothesis test. We're going to change the alpha, so that means we can't just use our confidence interval because that was 95%. This has an alpha of 0.10. So this is allowing a little bit more error. And recall that the more error we have, that can be bad because the type 1 error is increased, but it can be good because we have a higher chance of finding a difference if it's there. So it increases, by increasing our type 1 error, we decrease our type 2 error. They always go up and down together. So that's why we might choose to do this. Typically, I'll use a higher alpha value if it's something that's exploratory, or if I'm just kind of checking into it and may check into it again later, I might use a higher alpha value. Using this, so I'm looking, my null hypothesis is status quo, that is 0.5 or less. My alternative, where interesting things are going to happen, is if it's bigger than 0.5, that might mean I have to relook at the manufacturing process or how the computer chip is handling fluctuations in temperature. So using this, I have an alpha of 0.10. Now this is an upper tail test, so I want 10% of my error. It can all go in the upper tail. So 10% of the area in the upper tail, this is the one that I'm using. I still have 9 degrees of freedom, so I'm going to go down to 9, and my cutoff now is going to be 14.684. Now this is the cutoff for the critical value. So looking at this on a picture, I've got my chi-squared, I've got 14.684. Excuse my terrible writing, that was supposed to be an 8. Not even going to try to erase that because that's going to work out even worse. So this is my reject, and then fail to reject. So reject the null hypothesis is over here on the right. Fail to reject is over here on the left, and then there's a cut at 0 because the chi-square doesn't go below 0. So this is what my little picture is going to look like that I can go on and draw it myself. Now you can see the prettier version on the computer, but the reason I draw these out is so that you can see, and really, I mean, I know these are really, really nasty, but hopefully if you're on a test or working through a problem on your homework, you can feel comfortable to just draw this out really quick, just to get a quick visual. For those of you who are struggling with this content, sometimes a visual can really help to push you over the edge and understanding and getting a feel for what's going on. And for those of you who this is all really easy and making a lot of sense, sometimes a visual keeps you from making a dumb mistake. So hopefully this can be helpful. All right, so I've got my sigma squared sub 0. This is my null hypothesized value of 0.5. That's what the problem told me I'm comparing against. And then I just plug in my n and my sample variance from the data. So I literally go calculate the sample variance from the data. 0.7 is the same we had before. I get my chi-squared test statistic value is 12.6, and I'm comparing to this cutoff of 14.684. Because my chi-squared value is smaller than the cutoff, I fail to reject the null, and that is to say there's not evidence to conclude that the variance is larger than 0.5. I don't have enough evidence to make that conclusion. Or in other words, doesn't appear that there's enough evidence to conclude that there's a problem at the 90% confidence level. Using the p-value approach, I just plug in the p-value in this particular case. I would never, so this is this is trying to imply like where the p-value falls. This is a really, really loose approach that we would use if we have a table and that's all we're doing. again, we have access to R, so we don't need to use a table. This is saying that because the chi-square test statistic falls between these two critical values, the probability falls between these two probabilities, and because the probability following between these two probabilities is bigger than our type 1 error that we're allowing, we fail to reject. P is bigger than alpha. And it's true. If P is between 0.9 and 0.10, then P is bigger than 0.10. So we fail to reject the null. Again, how this works in real life, though, is we get a p-value from our computer, either through using the chi-square distribution in R, or if we're using software to do the test for us, it'll just spit out the p-value automatically. And then we compare to alpha. If p is bigger than alpha, we fail to reject. That is, we don't have enough evidence to say the null is false. Or if p is less than alpha, then we do reject the null hypothesis, and we do have enough evidence to disagree with the null. All right, so I'm going to quickly do two populations. This video is getting kind of long, but I do just have a few slides on this. So for two populations, we kind of talked about an example earlier. So when we're working with two populations, just like before, we're going to be comparing them to each other. Now, the deal with two populations is we always phrase sigma sub 1 as bigger than sigma sub 2 just because we can. So we're going to run either an upper tail test or a two-tailed test. We're not really going to look at a lower tail test. Now, why do we do this? The reason that we do this is because this F statistic only runs in one direction. So now we're going to use a whole different table, an F table, instead of a chi-squared table. Now, this F distribution is something that we are going to lean on later in class. We're going to keep coming back to this. Key pieces of the F distribution is that now we have two different degrees of freedom. So in our F, we're going to have two sets of degrees of freedom that we're looking at. P-values are the same. So the reason we like p-values is because now that we have a new distribution, well, we have to go find a new critical value and stuff like that. But p-values, I don't have to worry about any of that. If the computer spits it out, I just compare that to alpha. It's why a lot of people really prefer the p-value approach to the critical value approach. So sigma sub 1 is the variance of the first population, sigma squared sub 2 is the variance of the second population. And our test statistic is just the larger variance over the smaller variance. So whichever of your populations has a larger sample variance, you take that divided by your small sample variance. For the 2 degrees of freedom, because the test statistic is the larger divided by the smaller, we have a numerator and a denominator. So we'll call it the numerator degrees of freedom and then the denominator degrees of freedom. And it's just n minus 1 for the first population and n minus 1 for the second population. But don't forget, it's not just the first population that you read in the problem. In this particular context, n minus 1, or n sub 1 rather, is going to be the population with the larger sample variance. So whichever group has the larger sample variance, that's going to be population 1, both for the sample size and for the sample variance. So you're going to stick that in the first slot and plug in your values. So larger group, let's say one of the groups has a larger sample variance. Okay, that's going to be population 1. So I plug in that sample variance for S squared sub 1, and I plug in their sample size for n sub 1 and use that to calculate the first degrees of freedom. These always go in this order, by the way. So the F distribution degrees of freedom, especially when we get into R, the numerator degrees of freedom always come first, and the denominator degrees of freedom always come second. So let's say that instead of just looking at one thermostat and comparing it to a preset cutoff, we're comparing to a rival. So we're comparing our Thermarite thermostat to the Temp King thermostat and seeing if the variances are equal to one another. Now, because we're not specifying a direction of difference, we're just going to say equal or not equal to. And again, this is a good default for any test, unless you have a really good reason to run it in a single-tailed. Running it as a two-tailed version is what we do typically in real life. All right, so again, as we have 10 values for both of these, n sub 1 and n sub 2 are both 10. So for my degrees of freedom at the top, that's the larger variance. That would be n sub 1 minus 1, that's going to be 10. And then for the smaller variance, that's n sub 2 minus 1. Excuse me, n sub 1 is 10, so n sub 1 minus 1 is 9 degrees of freedom. And then, again, because the denominator is the same, we're going to have 10 minus 1 and 9 degrees of freedom in the denominator as well. So alpha is 0.10. So alpha over 2 is 0.05. And looking in our table here, this is what an F table looks like. I have my numerator degrees of freedom, which is 9. Then I scroll down to my denominator degrees of freedom, which is also 9. And then I find the area that I'm interested in. In this case, because it's a two-tailed test, I want to cut that alpha in half. So the alpha that I'm looking at is 0.05. And that gives me an F value of 3.8. So this is my critical cutoff value. If I draw out the picture, this is where my cut's going to be at 3.18. And then, again, everything to the right is reject. Everything to the left is fail to reject. And this is what I have. In fact, I don't think I have a pretty picture for this one. So you're going to have to deal with that. And then we're going to see is the test statistic s sub 1 squared divided by s sub 2 squared. Is it bigger than 3.18, or is it, and do we reject that they're the same, or is it smaller than 3.8? Do we fail to reject? So looking at the variances, again, I plug in the bigger variance on top. So s squared sub 1, the bigger variance is 1.768. S squared sub 2 is the second variance, 0.7. These are found from the data. I just run my variance calculation on the first data set and the second data set. That's where these come from. Then I plug this into my magic box, and I get 2.53 as my test statistic. Now my cutoff was 3.18, so because 2.53 is on the left side, that fail to reject region of that picture, I'm going to fail to reject the null hypothesis, and that is to say I don't have enough evidence from this sample to claim that the variance between Temp King's and Thermarite's thermometers are different at the population level. So recall, all of our statistical conclusions are regarding the population level. This is kind of important here because you can clearly see that Temp King's sample variance is bigger. So based on this sample, Temp King's is bigger, but this sample didn't give us enough evidence to make this conclusion for the population. So would I prefer Thermarite to Temp King? Well, I don't know. Maybe I'd go get some more data because this sample does seem like it's bigger. But I didn't have enough data to determine if it was by chance or not. Now, how would I determine a p-value in this? This was the critical value approach. Well, the honest answer is I use R, but for this, I can go to my table and I can figure out the different areas that could be in that upper tail. In this particular case, my F value fell between a 10% area in the upper tail and a 5% area in the upper tail. Now, because this is a two-tailed test, I'd have to multiply these by 2 to get the p-value for this particular problem. So in this case, you can see, because my F value is between the two F values, these are the two values I'm pulling out of the table, two-tailed tests, so I double these values to get 0.2 and 0.10. And because my cutoff is 0.10 and p is between 0.2 and 0.10, clearly p is bigger than 0.10, and we fail to reject the null hypothesis. If this looks complicated, it's because it is. So what do I do in real life? Well, if I'm doing this from an F distribution in R, I plug this into the F distribution in R, I give it the right numerator and denominator degrees of freedom, and I get the exact p-value, and then I still have to double it. This doubling the upper tail happens whenever I have a two-tailed test. So because this is a two-tailed test, I still have to double whatever my p-value is, but I'm going to get a number. So let's say I got 0.15 for the p-value. That's going to be a lot easier than this. It's between blah, 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 because I'm going to say, okay, p is 0.15, alpha is 0.10, 0.15 is bigger than 0.10, so fail to reject the null hypothesis. That is, there's not enough data to determine, or in this case, we didn't have enough evidence to determine that there was a difference between the two. I want to be careful. I said there's not enough data. It is true that more data will give a more accurate picture, but when I say there's not enough evidence, what I don't mean is that if I had more evidence, there's definitely going to be a difference because the sample variance from Temp King is higher than the sample variance from Thermorite. What I mean is if I had more data, these values are going to get closer and closer and closer to their true value. So there's a little bit of fudging. Like, these are not perfect values, and that's why we're not sure right now that Temp King has a higher variance, is because these numbers aren't perfect. So with more data, I'm going to get more and more accurate guesses at these numbers. And it may turn out that with a more accurate guess, this 0.7 goes up to like 1.2, and this 1.7 goes down to 1.2. It may turn out that with more accurate numbers, these are exactly the same. And that's what my information is telling me right now, is that with more accurate numbers, these could be the same. So if I wanted to determine a difference, I'd need to get more accurate numbers. That's why I don't say we don't have the data, and I slipped my tongue there. I apologize earlier. Because what we don't have is evidence. We don't have enough evidence. And part of that is the data, part of that is how far apart these are, and part of that is the confidence level that we're using this problem. All right, I apologize for the long video, but I did want to finish that up and not make a really, really short 5 or 10 minute video just talking about the two sample comparison. But this has been discussing how we test variances for just a single population against a constant, and how we test and compare variances for two populations to each other. In the next video, we'll be visiting all of this two population stuff and the 1 and 2 population variance comparisons in R and learning how to implement it there.